All right, it's about time. I suggest we get things going. Welcome, everybody. It's my pleasure to welcome Michael Burch today for the invited talk. Michael has studied computer science and mathematics in Germany and then went on to do a PhD in information visualization and visual analytics. And he then moved to the Eindhoven University of Technology before going to Switzerland to the University of Applied Arts in Chur. And yeah, I think he's one of the very prolific information visualization researchers. His CV lists almost 200 conference papers and other journal articles by now. And I'm happy to have him here today and to talk about eye tracking in visual analytics. So the floor is yours. Thank you.
Okay, thank you very much, Günther, for the introduction and also for the invitation. And unfortunately, I could not come because of this Deutsche Bahn problem that we had yesterday and today. But anyhow, as Günther said, my name is Michael Burch, and I'm actually working at the University of Applied Sciences in Switzerland at the moment. And what you can see here in the title of this talk is that I'm actually interested in two major research fields, which is eye tracking and also visual analytics. And we can combine both fields. That's the wonderful thing with that. So on the one hand, we could be interested in how users use visual analytics systems. And we get, for example, eye movement data. And on the other hand, we could use visual analytics to analyze the recorded eye movement data. And this is what the talk is actually about. So you see here on the very first slide, two adjacency matrices from an eye tracking study, actually. This is the eye movement behavior of 40 participants when they look at public transport maps. And you can see on the left-hand side, this left-hand matrix, it's actually not ordered well. So it looks more like chaotically, and you cannot derive visual patterns. So it's pretty hard to find some clusters or groups in the eye movement data with a perspective on the eye movement study participants. On the right-hand side, you see the same data set, but this data set got algorithmically prepared. The data is ordered. So the two-dimensional matrix data shows us some visual patterns. And this is actually something that we want to achieve with a visual analytics system. For example, we start with data. We want to visualize the data, but we also want to algorithmically process the data to see something in the data, like patterns, for example, to analyze it. And another question comes into play here is, how do the users behave when they look at this kind of visual representation? So what do their eyes do, for example? It's not about what do the users think about, but it's more on visual attention. So where do they look at? And can we learn something from this visual attention behavior to improve our visual analytics system, for example? So if we talk about visual analytics, we have to talk first about something that is called data science. So we have lots of techniques and theories from research fields within the context of mathematics, for example, statistics, or general computer science. And visualization is always, or in most cases, just treated as some kind of additional concept to rapidly detect visual patterns. But it's not only about the visual patterns. The idea is to remap those visual patterns to data patterns, to use visualization or visual analytics to analyze our data problem at hand, so the data that we have in the background, so to say. So visualization gets something like a powerful means to analyze our data, or to at least get support to see some patterns in the data. And this brings me to my research fields. So I'm working in this in these fields for, let's say, about 20 years now. So I started with something like information visualization, also software visual visualization, visual analytics, but I'm also working in graph visualization. And all of those fields bring into play visual representations of any kind of data, be it graph data, network data, software data, or whatever. And if you develop diagrams or interactive visualizations for these kinds of data sets, you are typically interested in the end what your users are doing. Are they understanding your visualizations, or do they have some problems? Is there some kind of design flaw in your visualization technique? And that brings you to a field which is user evaluation. So you actually learn about performance measures like the response times or error rates that your users actually have. And this is not everything. So we want to actually see where the people are looking at and for how long. What do they do when they make a mistake, for example, when they misinterpret the visualization, for example. And this brings into play a very powerful research field, which is eye tracking. So my research is actually visualization related. You see lots of visualization techniques. I developed several diagrams. I published them. Here you see just a few examples. So a bubble map based on eye tracking data. You see that here in this upper row, for example. Then we have software data here. It's like a hierarchy. It's a software, an open source software project with some kind of software metrics. You see here, for example, a development of a software system. This is the Linux kernel that got developed over several years of development time with more than 11,000 developers. So that's quite a lot. It's a visualization for that. And you also see something like emails or anything that is, for example, based on social context. So how people interact with each other and how they do that over time. There's one more concrete example. What you see here are several million flights in the United States in the years between 2001 and 2002. It's called a dynamic graph visualization. You see there's some kind of time axis that runs from the left-hand side to the right-hand side. You see that here at the bottom. And this visualization is a very condensed representation of the flight data in these 2 years. So what you see here at the first view, without understanding the visualization, but you see that there's a difference or change in the flight behavior in the United States in the years 2001 and 2002. On the left-hand side, this left-hand block here, you see the colors look a little bit brighter. Then there is a small gap, for example. On the right-hand side, you see there is a similar behavior, but the colors are not that bright anymore. And you can imagine yourself what happened here. There were the terror attacks at 9/11, and you see there were no flights at all in the US. And after the terror attacks, you see that there's a change in the flight behavior, and that remained for the rest of the year 2002. So this is a very scalable visualization, but why do we use eye tracking now, or why is eye tracking useful? We could try to figure out if my users understand the visualization. So I could give them a concrete task and try to find out where they have problems to understand this task. So I get their visual attention behavior, their eye movements, and I can try to figure out where these problems are. Here's an even more scalable one. These are millions of emails over time. So the problem here is that by just visualizing the data as it is, you cannot see anything. So you need some kind of algorithm that pre-processes the data, that structures or orders the data into some kind of clusters. You can see them here on the right-hand side. The clusters are the people who send the emails around. And if you do that, so if you combine algorithms and visualizations and interaction for sure, you see some wonderful patterns. So you can look at the visualization and try to understand the visual patterns, to map them to the data patterns, for example. And again, this is the power of visual analytics. So you have a combination of algorithms, of interactive visualizations, the human users, and something that is called analytical reasoning. So you try to figure out what is going on in my huge data set and how can I interact with the diagram, for example, to find even more patterns or to, let's say, confirm or reject hypotheses that I have before. But the big problem with visual analytics systems is that I do not know what my users are doing. I just have to rely on the visual analytics systems. That means I need some kind of user experiment. I have to ask the people, and in the best case, it's good to see visual attention behavior, also to see where and when people look at certain places. So visual attention, what is that? Visual attention is actually something that we pay all the time. So we wake up in the morning, we open our eyes, we pay visual attention to something, maybe to the coffee machine, or if we have a shower, we go to the bathrooms. We pay visual attention all the time in our lives. And the problem here is, or the good thing is, that visual attention depends on the task. So it depends on what you are planned to do next, so to say. And this has already been researched by a Russian researcher whose name is Alfred Yarbus. You can see here this figure that I brought in this talk. You see on the upper left part a painting which is called The Unexpected Visitor. So a man is entering a room and some people are sitting or standing around. And Alfred Yarbus examined how will the visual attention behavior look like when when the spectators get different kinds of tasks. So you see here a free examination task. That means just look at the painting. So your eyes are looking around a little bit. Maybe you look into the faces, to the room, to the chair, or whatever. But if you give them concrete tasks like estimate material circumstances of the family, you see that the visual attention behavior looks different than if you have it in the scenario number 1. The best case, you can see that in scenario number 3, if I ask you to give the ages of the people, you typically look at the faces of the people and how tall the people are to judge how old they are. You see that in the visual attention behavior. So again, the visual attention behavior depends on the task. And this is also something that is very relevant for visual analytics. So if you have a visual analytics system that shows your data, you are confronted by certain kind of tasks. It could be a search task, or it could be a correlation task, a comparison task, or whatever. You always try to solve a certain kind of task, and you use the interactive visualizations to find solutions to these tasks. And what you do is you actually do some of these, what we call scan paths. And these scan paths describe the visual attention behavior. Now I could compare a little bit. So we are talking about visual analytics, but actually there's something that is called information visualization. Let's say, when I compare information visualization with visual analytics, I oftentimes say that information visualization can be used to answer simple tasks, which is not quite true, but just to keep it simple, I see information visualization as a powerful tool to solve simple tasks, while visual analytics systems, they have more algorithms, they show bigger data, they have lots of interactions. They are powerful tools for complex tasks. So information visualization tools are typically based on a set of interactive diagrams, and visual analytics tools, they have more complex visualizations in the multiple coordinated views, for example. There are human-computer interaction techniques, or we have these large high-resolution displays, augmented reality, virtual reality, mixed reality, immersive analytics, and many more powerful technologies are integrated in the domain of visual analytics, and that typically is used to find some kind of patterns in the data, to monitor data, or to predict something based on existing data. What is the problem for eye tracking now? The problem is actually that this has an impact on what we call the visual stimulus. That's what we see actually. A typical information visualization tool could be based on simple diagrams, for example, a bar chart or a box plot or a line graph, something like that, just to keep it simple. So oftentimes we have a static stimulus, which is a scene that does not change over time. You look at the scene on a monitor, for example, on your flat computer monitor, you sit on a chair, and that has an impact on the eye tracking study. So you can just use a different kind of eye tracker than if you use an advanced visual analytics system where you have dynamic stimuli, for example, or you even have real-world stimuli. For example, you stand in front of a large high-resolution display, or you use something in virtual reality, for example. That, again, makes a difference for the eye tracking equipment, for the eye tracking devices, and also for the recorded eye movement data. Now on the next slide, I can show you a very simple example in information visualization, just to get started with some kind of task. Because I said it always visual attention depends on the task. So what we see actually and what we are going to solve in the visual stimulus on this, what we see actually. So on the next slide, you see actually a few letters or characters, a Q and C letters, and your task is find all the C characters and count them. So I can show you the next slide here. You see Q letters and C letters. So you are confronted by a certain kind of task. This is a visual stimulus, and your task is to identify all the C letters in this pool of Q and C letters. And you see this is quite difficult. So what you actually do is you scan the whole display, you make some kind of search task, and it's quite hard to identify the Cs. But if you, for example, use a visual variable, like it is often done in information visualization, so just use the color. So you color code all the C values in red, and all the Q values, they remain or they stay black. And I give you the same task again, identify all the C letters in this pool of all the letters. You get the impression that it's much faster. So you can easily spot the C letters. This is something that could be used in information visualization to visually encode outliers or anomalies, for example. For example, the bugs in source code. So you have a huge program or software project with lots of files. You could actually show bugs, for example, in a different kind of color, and then you suddenly, immediately, you can identify them. What's the good thing here? I can ask the same task again, and I make the pool of Q letters much larger. There are many more, and I ask again the same task. Is there, where are the C letters in this pool of Q letters? So it's again about visual attention. You are paying visual attention to that at the moment. You try to solve this task, this search task. At the moment, it is just a search task. If I color code the C letters again, you immediately see them. It costs you a fraction of a second to identify them, and here they are. Again, third example, I make it even bigger. You see what I do here. I have a pool of Q letters, and again, I asked you about the only C letter that I have here. So where's the bug in my source code? With this visualization, it's pretty hard to identify the outlier. But if I color code the C letter again, you immediately see it. So this is again about visual attention. Now you might ask yourself what happened behind the scenes. So I have no idea what happened there. And this is the power of eye tracking. So I could, while I did this small experiment with you, I could have recorded your eye movements, and then I get another problem then. I have eye movement data, which is quite complex. So I have to analyze the eye movement data later on. So you see, actually, the problem here with eye tracking in visual analytics is a twofold problem. On the one hand, I have the stimulus, like the experiment set up, my visual analytics system. Then I record eye movement data, and then I have the data. I need another kind of visual analytics system to analyze my recorded eye tracking data. So what we had here is something that is called pre-attentive processing. So this happens quickly, effortlessly, in parallel, and a little visual attention focused on the display. You see there is a little bit of visual attention. You look at the outliers, you see the C letters, the red ones, but you only pay attention for a fraction of a second, and then you get the C letter. That is something that is very, let's say, easy to analyze, because you do not pay visual attention over a longer time period, so to say. But if you look at a more complex visual analytics system, for example, you have longer, let's say, visual attention patterns, and that makes the analysis of this data more problematic. So pre-attentive processing is typically used in information visualization, but also in visual analytics. It's performed automatically on the entire visual field, detecting basic features of objects in the display. There are lots of these pre-attentive features. You see one we learned already, this is color, but there are some more. You can get that from the famous book of Colin Ware, for example, closure, line ends, contrast, tilt, curvature, size. You see many of them. So once you have a data set and you want to visualize this data set, and the focus is on the outliers, for example, try to use pre-attentive features to let them pop out. It's called the pop out effect. So the outliers or anomalies immediately jump into your eye. But what happens if we have something that is called a conjunction search? So for example, you have two data features that are visualized by two visual features. So for example, you could have the color, a blue color and a red color, or you could have the shape. You have these circular shapes and you have squaric shapes. So for example, if I ask you now a task, identify or find a red colored circle in both of them, in both diagrams here, it's quite hard. The problem here is that you have two different visual variables that encode the property of this red circle. The circle is a circle and the circle is red. Both of these visual variables carry at least one of the visual features. And the thing here is, if you make an eye tracking study, you will see that the people's eye movements, they are actually much more chaotic because your pre-attentive feature turns into a search task at the moment. It just not jumps into your eye, but you more or less have to scan the entire display to identify this red colored circle here, for example. And this is problematic for visualization or visual analytics. If you want to show your users something in the data, then make it pop out from the display. Just do not encode it with several visual variables in combination. That costs them a lot of time because people start a search task. The visual attention behavior gets much more chaotic than it should be in a, let's say, an advanced visual analytics system. There are even more of those simple experiments. I start with simple ones to show you the idea about visual attention here. So something that is called a boundary detection. You see in the left-hand side, we have red objects and we have blue objects. So if I asked you, is there some kind of boundary? You might say, yes, there's the upper region and the lower region. But if you look at the right-hand side and you try to find a boundary, it's quite difficult for you. But if you look at that, for example, you see that there's actually such a boundary as well. The objects on the left-hand side of this black colored line here, they are red circles and blue squares. And on the right-hand side, you only have red squares and blue circles. But you immediately see that this boundary detection task is much more complicated. For your visual attention behavior, that means on the left-hand side, you immediately spot the difference. But on the right-hand side, you have to search. You have to identify two different kinds of visual variables, and you have to identify in each individual object which kind of property they have to find the boundary. We can go even a step further. This one here, this task is one that is known from eye tracking experiment. It's called finding Waldo. It's a typical search task. So I show you here a visual stimulus, something like this here, and your task is to find Waldo. That's the name of this guy here. This is Waldo. I go one slide back. And if I show you this scene and your task is to find him, it's quite difficult. It's a typical search task. Now imagine you have a visual analytics system or an information visualization technique, and your task is, let's say, your goal is to build a visualization that shows Waldo immediately, that has to jump into your eyes immediately, like a pop-out effect. This is not a good idea because you cannot find him easily. But I can tell you, he's here. So if you look very closely here, you see there is Waldo, but it's quite hard to find him. What's the problem here? The problem here is that many of these visual patterns, the textures, so to say, they carry similar properties as Waldo itself, like the target object, so to say. So the visual attention here in such a scene, it would look more chaotically because you immediately turn into a search task. You have to search and you have to look very, very carefully. So my advice for you is, if you build a visual analytics system or an information visualization technique, try to avoid search tasks whenever possible. Design a visualization in a way that the people more or less immediately find what they are looking for. I know this is sometimes difficult, but you can make things more difficult than they actually are. So be careful with that. Another wonderful thing that we can find out with eye tracking is something like this here. So you see here a sequence of XY coordinates, 21 XY coordinates, and I can ask you, this is some kind of data, sequential data or trajectory data, so to say. I could ask you, is there some kind of pattern in this data? So what you, if you plan to solve this task, what you would immediately do is you take a pencil and try to draw these points, these two-dimensional points, maybe on a piece of paper. And if you do something like this, you get something like this here. So you see, if I draw all these 21 points on a piece of paper, I get a visualization of my sequential data, and that looks like a tree. But the problem here is now comes into play is you can only say that this is a tree if you have ever seen a tree in your life. So experience plays a big role in visual analytics. So if you want to identify visual patterns in a data set that is visualized, you have to know what the visual patterns are standing for. If you have never seen a tree in your life, you would never say that this is a tree shape. So this is very important. So if you visually encode a data set into some kind of visual depiction, you have to know, you have to have some kind of experience about the visual patterns that you create. Otherwise, your eye movement data would not be meaningful at all. Then there's something that is maybe a lot of you are familiar with, which is called the Anscombe's quartet. So I can give you 4 different data sets, for example, with nearly identical, simple descriptive statistics, but it shows the power of visualization. So I can plot these data sets visually, or I could use statistics to show if the data sets have some kind of similarity. So here you have the 4 data sets. You see them 1, 2, 3, 4. You have XY coordinates again. You have a set of data points, so to say. If I look at the data in this table, they look very different. So I could scan this table, but actually I do not get a lot of insights about this, let's say, more or less randomly looking data. So maybe I ask someone who is familiar with statistics and I say, please compare these 4 data sets for me. And the researcher from statistics comes back and says, okay, I looked at your data and actually the mean value of X is exactly 9 and the sample variance of X is exactly 11 and so on and so forth. And you see there's even a linear regression line, which is y is 3 plus half of x, for example. So it's very similar. So the statistics researcher would say all of the 4 data sets are exact or are the same, or at least are very similar. And that's everything what I can tell you. So you might be confident, but if you look at the visualization of this data, here you see again our 4 data sets, our XY coordinates. You see from a visualization perspective, if you ask a visualization expert, the visualization expert would never say all the 4 data sets look exactly the same. They are very different. All of these 4 data sets have different visual patterns. And why is that important for eye tracking? What we actually do here is a task in the background. So we do a comparison task. We have 4 different visual patterns here. You look at them and I ask you, tell me the difference of these data sets. And to tell me the difference, you look at all of the patterns individually and you have to compare them. You store them in your short-term memory for a little bit, for a little while. Then you look at the next one, and the next one. And while you do that, you do some eye movements. You look at them, you look at the characteristic features, for example, this outlier here, and so on. And this is how you do the comparison. You see again, you have a task, something that is in the background. You do all the time, you try to solve tasks when you look at visual scenes that we call visual stimuli in eye tracking research. Now let's go a little bit back to the data. Everybody, if you have seen this data explosion, here are just some numbers. So we have around 250 million photos uploaded to Facebook each day, which creates some kind of huge data set. There are lots of visa transactions worldwide each day, or 200, billions of emails have been sent every day or are sent every day. And this brings into play the power of visual analytics. So on the one hand, you have the visualizations that I've shown you. So you have lots of tasks in the background to solve visually. But on the other hand, visualization alone is not powerful enough. You need algorithms. You need filtering algorithms, clustering algorithms, dimensionality reduction, and so on and so forth. Anything from the algorithmic perspective that is needed to find patterns in the data is good. So we take everything in visual analytics that leads to some kind of goal to identify patterns in the data. So here are some examples from my research, or also here from Danny Houghton, for example. Edge bundling is a powerful or a famous technique from graph visualization. So these are techniques that are useful to visualize any kind of abstract data, for example. So visual analytics, just for a definition, if you have never heard about the field of visual analytics, is the science of analytical reasoning facilitated by interactive visual interfaces. This definition is given in this famous book by Thomas and Cook from 2005, Illuminating the Path. And visual analytics can attack certain problems whose size, complexity, and need for closely coupled human and machine analysis may make them otherwise intractable. So with classical information visualizations or classical interactive diagrams, you typically will not reach the same goals as with visual analytics systems that can even make use of high resolution displays and things like that. So a good thing with visual analytics is that you can actually start generating hypotheses, new hypotheses, when you have a totally unfamiliar data set, a data set that you have never seen in your life before. So you start to hypothesize around a little bit, and you want to prove or confirm or reject or refine these existing hypotheses. Let's say you use visualization to look at them a little bit, or you present the information, for example, about a known data set to another kind of audience, like I do it at the moment to you. So I present you some information. And the good thing with that is each time you try to confirm or reject a hypothesis with a visualization tool, you do visual attention, because if you want to confirm or reject the hypothesis, you start solving tasks. It depends on the hypothesis. If your hypothesis is the maximum value in a bar chart is 1000, your task is a comparison task, because you have to compare all the bars in the bar charts one after the other to identify this maximum value. So each time you try to solve something, you are actually linked to a certain kind of a task, and that guides the visual attention, which can be actually measured or recorded by an eye-tracking device. Another simple example from information visualization, maybe you have seen that before. Here are the famous pie charts. You see, I have three different scenarios for you: the left-hand side, the center one, and the right-hand side. And your task is to sort the values in decreasing order. You see on the left-hand side, it's quite difficult. You cannot say if the black arc is larger than, let's say, the yellow one. You might just guess, okay, it might be a little bit larger, but it's quite difficult. And the same for the right-hand side. And even for the center, it's quite difficult. So the problem here is that actually the visual metaphor is the wrong one. The pie charts are quite bad for this kind of task. For comparison tasks, never use a pie chart, but instead use a different kind of visual metaphor, which is a bar chart. Here you see the same data set that we have seen in the pie chart before, now visualized with the bar chart. And I can ask you now the same task again as before. Sort the values in decreasing order. And even if you look at this center diagram here, where it was quite difficult to order them in the pie chart, even in the bar chart, it gets easy to order them. You see that the yellow one is the tallest one, followed maybe by this light, the brighter one here, and the red one, and maybe the one labeled with D is the smallest one, so to say. So the task to solve the task is much easier with this bar chart than it was with the pie chart. And this is oftentimes the case also for complex visualizations as we use them in visual analytics systems, but we do not actually know what the users are doing. Where are the design flaws? What is the problem behind the scenes? If you use eye tracking and you look at the eye movement behavior, you can get an idea about what the people are doing while they solve a certain kind of task. So here you see both of them again on the same slide. I will give you the slides later on. You can try this experiment by yourself if you like. Here, this is a very simple visualization, but this also occurs in more complex visualizations. If you cannot understand simple visualizations, the problem will not get easier for more complex visualizations. So always, if you have data visualized, imagine yourself in the role of the user. Is the user able to identify the visual patterns? Or, in other words, is the user able to solve the task that is in the background, so to say? There's always a task that guides the visual attention. So what we typically can do is we can conduct some kind of user experiment. There are thousands of user experiments in information visualization, and what the researchers typically do, they record response times and error rates as some kind of dependent variables. And those dependent variables get statistically evaluated, you know, these ANOVA tests and things like that. And the hypotheses get confirmed or rejected that we have stated before we started the user experiment. This is, I would not say it's not easy, but it's, let's say, it's standard. It's it's a standard approach to do it, something like this. There are hundreds and thousands of user studies just looking at these measurements here, response times and error rates. The problem gets more complicated if you are interested in the eye movement behavior. Here, this is an example from a real eye tracking experiment that we conducted. So I showed the participants 5 bars in a bar chart, and one of the tasks in the study was, in the eye tracking study was, find the second smallest bar and tell the encoded value. It's not the smallest or the largest bar. That would be easy because pre-attentive, the tallest and smallest one, this pre-attentive processing I showed you before. But I asked them about the second smallest bar. So what I have to do is I have to identify the smallest bar and then the second smallest bar. And before I can do that, I have to look at all the bars. I have to identify what is the value here. I have to compare them. And then I identify this bar here as the second smallest one. And it's even more. This task is twofold. I asked about the encoded value. So it's not that I identified the second smallest bar, but I have to read the value on the y-axis as well. And you see how the visual attention behavior looks like. It's not something very, very simple. These are called scan paths, and these scan paths, they consist of fixations. These are these circles here. The different colors are different study participants, by the way. The sizes of the circles is the fixation duration, so how long the people looked at a certain point of interest. And these lines are called saccades. That these lines, the saccades, tell you where the people looked next. So it's a trajectory visualization, so to say. It's a typical scan path visualization. And now you have eye movement data overplotted on a very simple bar chart. Now you see the problem here. We have a visual analytics system with a very complex visualization. You have many users. You have long durating tasks, several minutes, for example. If you use such a visualization for your eye movement data, you will not see anything at all because it will be completely overcrowded. So you need other kinds of visualization techniques to analyze your eye movement data. But this visualization is just to give you an idea, an impression, what is going on if we ask people such a simple task like finding the second smallest bar in such a bar chart. So this is the visual attention pattern that you get from such a very simple experiment. So what is the problem here? The problem is that we have to do with so-called eye tracking metrics. And space and time dimensions are the major eye tracking metrics that we have to deal with. The space is that we see. It could be a two-dimensional stimulus like a computer monitor, or you could even walk in the real world. So you have a three-dimensional stimulus. For example, you go into the supermarket and you buy something, some product. So the supermarket owner might be interested in the customer behavior. So where are the customers looking at? So then you have a three-dimensional real world situation, and also there you can do an eye tracking experiment. But again, the problem is that you have spatial data, space and temporal data. The data is your eye movement behavior is changing over time. And that makes statistical evaluation much more complicated than it is the case in these traditional user experiments where we have the response times and the error rates. So that is actually illustrated in this simple pipeline here. On the left-hand side, you see there is a research question in the background. So if you start developing your own tool, for example, you have a research question or several of them in the back. So this research question guides your research, so to say. In the visualization domain, you have a stimulus, something that the people see. And again, you have a task or several of these tasks. Then you can do a standard user study. And we talked about that already. You can do a statistical evaluation of your study data. But if you go, if you look at the bottom row here, you see if you use eye tracking, you get the spatial temporal data, and you also get other data, participant data, physiological data, so to say, like data about the body of the participant that could also be used as some kind of, let's say, getting insights in the visual attention behavior or in the user behavior, I have to say. So here you see that the statistics is not useful anymore because eye tracking data is much more complex than the data from these traditional user studies. And that also brings into play different eye tracking devices. There's not a single eye tracking device that could be used. You have to first identify what is your stimulus, what do you show the participants, and what is the environment in which these stimuli are actually used. So you have to think about the design of your eye tracking study before you can decide about an eye tracking device. And there are lots of them. I talked about them already a little bit. So, for example, you could have a mobile eye tracker. That means you are mobile as a participant. You can just walk in a supermarket. So you actually are freed from the laboratory. You can just freely walk around, look into the shelves, and try to find some products that interest you and that you want to buy in the supermarket, for example. Those are typically sometimes also called head-mounted eye trackers because you can put them on your head, like glasses, for example, as you can see here on the left-hand side. Or if you, for example, if you plan to have a visual analytics system on your computer monitor, you do not need a mobile eye tracker. You can use it, but the better way is you use a stationary or what we call a remote eye tracker. That means your visual analytics system runs on your computer monitor and you just sit in front of your monitor and look at the stimulus, so to say, and the eye tracking device records your eye movement behavior, your visual attention. So you have an additional dependent variable in form of eye movements, which is called spatial temporal data. And the big challenge in eye tracking is that the statistical evaluation of such data with the goal to find common visual task solution strategies among the participants is quite challenging. It's really, really hard because the people never do the same strategy. So for example, if I send 100 people to a supermarket, buying a bottle of Coke, for example, everybody solves this task differently. That means everybody of these 100 participants has different kinds of scan paths and walks differently through the supermarket. So the first thing, or the first problem, the first challenge that you get is you have to align your eye movement data. You have to, let's say, transform them, you normalize them, that you find similar strategies among your participant groups. And that's always the same. Eye tracking data will not look similar for every participant. You have to identify the similarities first before you actually can visualize them. So visual analytics is one solution again. So you see, I started with visual analytics. I showed you some usefulness of eye tracking applied to visual analytics. And now I can use visual analytics again to analyze my eye tracking data. So I have a data set, which is spatial temporal data. So at least 2 data dimensions I have. And then I need a powerful technique to find insights in my data. So I have algorithms, can be any kind of algorithm that is useful for your eye tracking data, for example, multiple sequence alignment, dimensionality reduction, clustering, whatever you have. You have interactive visualizations. You have the human user and you have HCI, human computer interaction. So you have interaction techniques. And so that means visual analytics combines lots of application fields. It's an interdisciplinary or multidisciplinary field of research, and that is actually the power of visual analytics, and that makes it so useful for eye tracking data. We can even go a step further. You see here, I do not only have the eye tracking data or the eye movement data, I must say, we also have additional data. For example, I just call it qualitative data. You could have verbal feedback. So the participants, for example, could talk. You could have something like a talk aloud or think aloud eye tracking study. The people talk while they pay visual attention to something. They talk about how they solve a certain task. You could have personal data, like the gender of the participants, the age or experience levels. How familiar are they with the visual analytics systems? How familiar are they with visualization and things like that? You should write that down before you start an eye tracking study. But also during the eye tracking study, you have gestures. People might move their hands, or maybe they are nervous. They are moving around all the time. So like anything that is related to body movements, for example, could be interesting. Or noise. People speak. They might be stressed, something like that. They might do something like something like this. So these are these noises. So you can record them to use them later on in your eye movement data or your visual attention data analysis. But even more, you have physiological data. You can, for example, measure EEG. So like say brain waves, something like that. Whether the people in which brain regions are activated at the moment. So for that, you need additional devices. You could have something like pupil dilation. So if people concentrate on something, they have different kinds of pupil dilations than if, let's say, just look around for let's say, a few fractions of a second. You can measure the blood pressure, or you can look at galvanic skin response. So people are sweating, they are nervous, for example, if they are confronted by a certain kind of task. You see, apart from the eye movement data, you can include in your study, in your user study, you can include additional data sources. And again, that makes the analysis much more complicated. So you don't only have the spatial temporal eye movement data, but you have additional data sources to analyze later on, always with the goal to find insights in the, let's say, user behavior, because your goal might be to improve something, to improve your visual analytics system, or going back to the supermarket scenario, you want to improve the placement of products in your supermarket. So you want to learn something about the behavior of your customers to improve your selling strategies. So you want to learn if the products are, for example, wrongly placed in your supermarket. To come to an end, my 45 minutes are over, I think. We have hundreds of visualization techniques for eye movement data. A few years ago, I was co-author of a state-of-the-art report on eye tracking and visualization. Some powerful techniques are those here. Maybe you read about them if you're interested in them. These are the gaze stripes. So you see here very small thumbnails. Each line is one participant. And these thumbnails, these very small, look like stamps, very small ones, generate a texture pattern. And by this texture pattern, you can see the differences and similarities in the visual attention of the people over time. A similar tool is something like this. It's called ICG. You can see here a space-time cube. It's actually an animated cube. There's a video for that, and I can also give you the link to the video later on. But again, it focuses on visual attention behavior. Then there is something from information visualization, a tool that is called the AOI rivers. You see here the visual attention to different areas of interest. In this scenario here, you see, for example, that the visual attention to this light blue area in the stimulus gets more and more over time. When the time progresses, more and more people are interested in this light blue area here. So with this visualization technique, you can see on one view where and when the people pay visual attention to a visual stimulus. And there are even many more. The most popular one is the so-called visual attention map. You can see a few examples here. For example, when I confront people with a reading task, you see I give you a task to read something, a text, and then I can actually visualize the eye movement behavior. So how do people read the text and where do they stop for a longer time? So where is the fixation duration the highest and where not? So here in this scenario, you see obviously that most of the visual attention was paid in the upper row of this text and not in the title, for example. Or if you look at the person here, you see that there are two different kinds of visual patterns. So the one on the left-hand side looks a little bit different than the one on the right-hand side. But again, a single visualization technique will not help you to, let's say, analyze your eye movement data. There are too many data properties included. That means you need a combination of interactive visualization techniques and algorithms to understand the recorded eye movement data. And that makes visual analytics so powerful for eye movement data. So it's the combination of all of these concepts from this multidisciplinary field. Okay, here's a video that is, I will not show that, but I will share the slides with you so then you can have a look at this 5 minutes video about the gaze stripes. Okay, with that, I would like to thank you for your attention, and I hope I could give you some ideas. I mean, this is a huge field. This is just the peak of the iceberg, just to give you a few ideas about visual analytics, eye tracking, and again, visual analytics applied to eye tracking. Thank you, and I'm open for questions.
Thank you for the nice presentation. Are there any questions in the room or online? Maybe while people are thinking about it, there's lots of talk about, you know, immersive visualization now, and you also touched upon it slightly at the beginning. But I could imagine that you have different requirements or different challenges for eye tracking in these scenarios. Can you maybe say a little bit more about that?
What do you mean immersive analytics, something like that? So a combination of virtual, augmented, mixed reality.
Exactly, yeah.
Yeah, sure. There are lots of challenges, but still, one of the big challenges is that that you get eye tracking data, and you have to interpret the eye tracking data in a certain context. So, for example, people actually run in a physical room or in a virtual room, depends on the setup. And the problem is that you never know what the people are thinking at this in such a scenario, but you only have the visual attention of the people. So it's quite difficult, let's say, to analyze the data in such a challenging context. So this is what I think is the problem here. The technological problem of recording the eye movement data, I think it's actually not that of a big problem anymore.
All right, thank you. Any more questions?
I have a question.
Yeah.
First of all, thank you for the talk. I got a question. Like, I tried to record eye data once with a VR head-mounted display, and there was a license of Tobii, and you could only get like the coordinates out, and you need to pay for it.
Exactly.
But my question is like, what do you like recommend to what you should at least record, the bare minimum? And my second question would be like, how do you process this data? Do you like have like some frameworks, or is your own work? Like what general advices?
Yeah, thank you for the question. I think the least kind of information are actually the coordinates and the fixation duration and the stimulus. So typically they record a video of that. So the frames, actually every frame, the video consists of lots of frames, and every frame actually has, let's say, the fixation of the eye movement study. This is the least information you need to, let's say, find something out about visual strategies that the participants apply, let's say, to find out about a design flow. And your second question was again about the frameworks. we actually are in the beneficial situation that we develop our frameworks ourselves in our research field. I typically work together with the University of Stuttgart. This is where I let's say, did my postdoc for 8 years, and I have lots of colleagues there working in eye tracking and visual analytics, and we actually built our own software. But you are right, the licenses are a big problem, and this is actually how companies like Tobii, you mentioned Tobii, how they earn their money. So they sell these licenses, and this is how they make money out of that. Or one more, let's say, one more thing to make money out of it.
If I may ask one more question.
Yeah.
These frameworks you developed, is it like open source or testable, or is it like only for internal use?
At the moment, it's for internal use, but if you're really interested, we can have a meeting and we can try to get your data in our frameworks, then you can use it. But it will cost, typically, the problem that we have is that you have a different kind of data format. So it's not the tool is not the problem. So if the tool is actually running, it's good. But the, let's say, the linking to your data format, that is the biggest burden that we typically have with other people.
Okay, thank you very much.
But again, if you're really interested, we can have a meeting again, and I can try to share my ideas, and we can try to get it running and see what is in your eye movement data.
Yes, sure.
I have a question about cognitive load estimations based on eye tracking measures. You already mentioned pupil dilation, but from your experience, what would be some measures that we can use from the eyes that give us a pretty reasonable approximation of maybe the cognitive load a user is experiencing?
This is it's actually a difficult question. So the first thing is how do you define the cognitive load? But what is your impression? Is it like stress, or how long I'm thinking about something, or is it, let's say, the brain activity? So you can actually measure brain activities, for example, and that could be matched to cognitive load. But in my opinion, you cannot derive a lot of, let's say, insights from the cognitive load. This is at least my opinion.
Okay, thank you.
So what is your impression about what is cognitive load for you?
I mean, cognitive load is things that you said, like stress level,
Exactly,
the
yeah.
amount of processing I'm doing to maybe understand a more complex task.
Exactly. What you already mentioned is you could measure the pupil dilation and, let's say, the galvanic skin response, or let's say you combine different other physiological measures. It's not a single one, but several more. And then you look at several of them in combination. But still, if you have all of them, if you had all of them, it's quite hard to analyze cognitive load.
Okay, thanks.
So my research is typically on only the visual attention behavior, not on, let's say, what people, how they are stressed or what they are thinking about. This has a name in in the eye tracking research field. It's called the eye-mind hypothesis. Or it's related to the eye-mind hypothesis. That means, are we really thinking about what we are looking at? So if you have study participants in your eye tracking study, you never know if they really think about what they see. Maybe they think about their last holidays and not about your visual analytics system. And so you cannot look inside the brains of the people. That is the big problem. It's something like science fiction at the moment, but I believe in a few years, it might be possible to understand, let's say, what the people are thinking. It's related to cognitive psychology.
Mm-hmm. Okay, thank you. I'll look into that.
Yeah.
We have one more question in the room.
Yeah, thanks for the talk. I was wondering if you or if you have ever conducted, or if you know of any research of eye tracking in the domain of explainable AI, to see basically whether humans focus on similar areas as a machine learning model.
Günther, could you repeat it? It's
Yeah,
not.
yeah. So the question is if you are aware of any eye tracking work in the domain of explainable AI.
Yes, I'm aware, but I cannot tell you. So I'm actually working myself in this domain. But again, if you are interested, we can have a meeting and I can talk about that with you in an individual meeting. So, but there will be more work in this domain. Explainable AI is a field that maybe exists for 5 years. I don't know, it's quite young. But in my opinion, before eye tracking will take place in this field, the field itself has to develop a few years, and then you will see more and more eye tracking studies in this field.
Okay, thank you.
All right, thank you.
I also have a question.
Okay, yeah.
For the patterns you showed last, so if you have this aggregated view of the data, which is on this screenshot, are the patterns typically searched by human, or are there also automated approaches to this?
Which one do you mean? The last one here, this one? No.
Where I showed this heat map-like visualization for the patterns.
This one?
No, I think it was even more before, in the middle of the.
In the middle?
Yeah, before that, like if we go a bit.
Which one? This one?
No, before that, where I show the red and blue heat map.
I think the one with the emails.
Yeah,
the emails. Yeah, sorry. Okay, now I know it. Sorry. This one here.
Yeah, this but it applies to all aggregated visualizations you showed. Are these meant to be read by a human or by a machine, basically? So the patterns.
You can do both ways. This one that you see here is done by the machine. So we automatically clustered that into most frequent conversations. So here are the person groups who most frequently send emails around. So these are the clusters, but you could also do that, let's say, user-driven, so human-driven. So you can build the clusters on your own. This is an interactive visual analytics system. This is just a static screenshot. But both ways are possible. But that's always or should be integrated in visual analytics systems. So you can have the user decide. The decision can be done by the users, by the exactly the explorer, so to say, or it can be done automatically, or at least semi-automatically, that you let the machine do something for you, and then as a user you say stop. I look at that and I want to go one step back, for example, or refine some parameters, something like that. This is visual analytics. It's a combination of human and machine, so to say. And this here is automatically done by the machine only. Is that your question?
Yes, thanks. Very interesting.
Yeah. This one here, by the way, is random. You see this is the one on the flight behavior. On the y-axis, there are the airports, and these are the XY coordinates of the airports in the United States. So we just, let's say, flattened the two-dimensional geographic map into the 1D. And then you get the order of the airports, and then you already see some kind of patterns. But we could even go a step further and cluster the airports. But here's already some kind of spatial information, which is the geography. You understand that? So the airports are somewhere on the geography in the United States, and you can use the geographic information as some kind of placement on the y-axis. So you flatten the two-dimensional information into a one-dimensional information. And that is the reason why we did not have to order this visualization, because there is some kind of useful order in the beginning. But the better option would be to also apply a clustering here. Then you might see even more patterns. This is the power of visual analytics. You can look at an automatically generated solution, or you could say, you could intervene as a user and say, no, I'm not confident. I want to refine some parameters and see if I'm better. You have two options there. But again, visual attention is always in the back somewhere that decides what is better. Okay?
Thanks.
Thank you. And I think we can wrap it up at that point. Thanks again for the very nice talk and taking the time.
Okay, thank you.
Thank you. Thank you. Bye.
Can I share the slides with you if you like?
Yeah, you can send it to me. Yeah.
Okay, good.
Yeah. Thank you.
Thank you. Bye.
Bye.